Hi, let me take a few minutes and go over this handout where we revisited our class experiment. So, first of all, the parameter P is the proportion of students who can distinguish Dasani and Ice Mountain. Some of you were really careful and wrote it as the proportion of AP statistics students. That's all fine and good. The only thing that people lost credit for, some people said that this was the proportion of students who were able to guess the difference. And it's not about guessing. I'm interested in students that can actually distinguish the difference, not just guess it. So here's the null hypothesis value. The alternative hypothesis value should be P is greater than 1/3 because we're interested in doing better than strictly random guessing. So I gave you a point for having the P and the greater than, and then a point for using that parameter of 1/3. There were a few people that wrote greater than or equal to. Really, it should be strictly greater than. The equal to is the null hypothesis, but if you did that, I just scratched out the equal to. So in terms of the conditions, randomness is met because some people just wrote that we have a random sample. I didn't count that wrong, but notice up here at the top, we actually have a simple random sample. I really did take a simple random sample, so I drew an arrow down to this line and put SRS for you. If you have a simple random sample, you really should state that. So that's met. Independence, though, is not met. So the correct way to do this is to take 10 times the sample size. That's 250. So I gave you a point for doing that. But understand, for the independence condition to be met, the 250 has to be less than or equal to the population size, which here is 133. So I just wrote that 250 is not less than 133. Some people wrote the less than or equal to symbol and put an X through it. Some people wrote that 250 was greater than 133, so that would certainly imply that the condition is not met. So normality is not met. Guys, a number of people said that normality is not met because 25 is not greater than or equal to 30, so the central limit theorem doesn't apply. Well, you lost 2 points for doing that because the central limit theorem doesn't apply in the first place, because this is a question about proportions. This is not a question about means. So you have to take n times the p, the population proportion that's being assumed in the null hypothesis. So you have to use 1/3 here. And you have to take those values and multiply them out. If you take 25 times 1/3, you get 8.3 repeating. So you need to show that value. Here, 25 times 1 minus 1/3, that's 16.6 repeating. So you need to actually calculate those values. I took off a point if you didn't do that. So it's important that you're comparing those values to 10. These need to be greater than or equal to 10 for the normality condition to apply. Now understand, you should be careful how you write the inequalities though, because 8.3 is not greater than or equal to 10. So you could put the greater than or equal to 10 symbol, but then you'd have to cross it out. Or you could just write 8.3 is repeating is less than 10. That would be fine, and that's explaining that this condition is not met. There were a few people that instead of using 1/3 and instead of using 2/3, they put in 0.33 and they put in 0.66. I would be careful rounding here. If you're working with a proportion, you need to use the exact population proportion, which is 1/3. I would have put it in my calculator that way. So also, there were a number of people that instead of using 1/3 and 1 minus 1/3, they used the sample proportion. They used 6 out of 25. 6 out of 25, that turns out to be 0.24. There were a number of people then that did 25 times 0.24, and then they did 25 times 0.76. I did take off a point for doing that because you should be testing your conditions by using the null hypothesis value. That's the value that you use when you actually conduct the test itself. So, guys, here is the z-score that you would get. Here is the p-value that you should get. I'm going to calculate that here for you now. So stat under tests, this is a 1 proportion z-test. So we should enter the null hypothesis value. And you should enter the null hypothesis value as 1/3. I'm going to put it in as 1 divided by 3. That's really the most accurate way to do this rather than typing in 0.3 or 0.33 or 0.333. So the value of x, the number of successes we had, was 6 out of a total of 25. This is a greater than alternative hypothesis. So there's where the z-score and the p-value come from. So those were each worth 1 point. Something to notice, though, if for some reason, this only happened to a couple of people, if you wrote that the p-value is less than 1, not p-value, if you wrote that the proportion is less than 1/3, if you had the wrong alternative hypothesis there, you would have gotten a different p-value. I might have given you credit for that p-value if you had the sign wrong here. So interpreting the result in context then is really important. There's a total of 6 points here. So, guys, you need to be comparing the p-value explicitly with the level of significance. In this case, 0.05 or 0.01, it really doesn't matter. Using the p-value, which is greater than 0.05, that's 3 points right there. You must explicitly show that comparison either in words or in symbols. So that's 3 of the points. Then you must say whether or not we can reject the null hypothesis. We can't reject the null hypothesis. So that's because the p-value is much larger than any reasonable level of significance. So now you have to write about the alternative hypothesis in context, and you really should use the word evidence. In this case, I did not reject the null hypothesis, so I have no evidence that suggests that the alternative is true, that suggests that the proportion of students who really can distinguish between the brands is more than 1/3. That's what the alternative hypothesis says. When you interpret your statistical test, you really need to write about it in context, and you need to be writing about it using words involving evidence and using a description of whether or not you have evidence of the alternative hypothesis. So that's the set of correct answers, and that's how I scored it. I want to use this, though, as an opportunity to review what the p-value calculation represents. So if you turn your quiz over, here it is. I put this on the back of your quiz, reviewing the definition of a p-value. This is something that you need to know for your test, for our unit. You need to know this for the AP exam. You'll see this on some of our AP review questions for this unit. So the definition, the p-value of a significance test is the probability of a sample statistic. So that could be a p-hat, that could be an x-bar, a sample proportion, or a sample mean. A sample statistic as or more extreme than the one observed under the condition that the null hypothesis is true. So we are assuming that the null hypothesis is true, and then we're calculating the likelihood of the sample statistic that we've seen. So if it's really unlikely, if the null hypothesis is true. So if we get a really small p-value, that suggests maybe the null hypothesis isn't really true. So in the context of our experiment, the p-value is the probability of a sample proportion as or more extreme than the one that we observed. We observed 6 out of 25. Under the condition, or given that the actual value of the population proportion is 1/3. So the condition here is that 1/3 is the truth. How likely is a sample statistic as or more extreme than ours if the truth is really 1/3? This really is a conditional probability. So to calculate the conditional probability, in this case, you need to calculate a z-score. So the z-score, we're going to take our sample statistic of 6 out of 25, subtract what we believe the truth is, that's 1/3. So this really is a conditional probability because we are using that condition in the calculation of the z-score. Then we need to divide by the standard deviation of the sampling distribution. Once again, we are using the value of p that is assumed in the null hypothesis. 1/3 times 1 minus 1/3 divided by the sample size. So if you put this into your calculator and simplify it, and again, for the greatest level of accuracy, you really do need to simplify this by using the fractions. I wouldn't round at this point. So I'm going to take my numerator, which is 6 out of 25. I'm going to subtract the true value of 1/3. And then I'm going to divide by the square root of my 1/3 times 1 minus 1/3. That would be 2/3. and I'm going to divide by the square root of my sample size. So there's the z-score. Under the condition that the null hypothesis is true, the z-score is negative 0.99 essentially. So the p-value really is the likelihood then that we get z-scores that are as or more extreme than this one. Z-scores that are greater than, again, the alternative hypothesis is in the greater than direction, greater than negative 0.99. Now, notice something really special happened in this case. To try and tie some things together, think back to the empirical rule. These are z-scores, and we're working with the normal distribution here. So you should know how to find the likelihood of a z-score that's greater than negative 0.99. For all practical purposes, folks, that's a z-score of negative 1. So let's look at the normal distribution. Here is our mean of 0 for z-scores, our standard deviation of 1 for z-scores. So remember what percentage of the data is within one standard deviation above or below the mean. That's 68% of the data. Essentially, we have two regions of 34% each. So that means that 32% of the data is accounted for in these two tails. So if I divide that in half, each of those tails is 16%. This is just the empirical rule. Well, notice negative 0.99 for all practical purposes is at negative 1. So I'm looking for all of this area here. Well, 34% plus 34% plus 16%. Shockingly, that comes up to 84%, and that explains the p-value that we got, 0.84. So if you wanted to use your calculator, this is where you would use the shade norm command. I'm not convinced that you need to do this. I think it's more clever to use the empirical rule. If you're going to use the shade norm command, I would run the norm window program first. Then, fine, you can go second variables and draw shade norm. So you can put in negative 0.99 for your lower boundary, and you can put in 10 for your upper boundary. And you can see it, but again, you're going to get nearly exactly the same thing. There's the 0.84. So I wanted to take the opportunity to review the definition of a p-value. A p-value really is the probability of a result as or more extreme than what we've seen in our sample if the null hypothesis is true. So that's why if we see a really unlikely probability, then maybe the reason it's so unlikely is because the null hypothesis that we assumed is true, maybe it's not really true. That's why when p-values are very small, less than 5%, less than 1%, we reject this null hypothesis. Of course, in this case, we got a value that was very likely. If the null hypothesis is true, we got a p-value of 0.84. A sample result as or more extreme than our 6 out of 25 is quite likely if the null hypothesis is true. We have no reason to reject the null hypothesis, and then in turn we have no evidence of the alternative. We have no evidence that people are doing any better than just by strictly random guessing. There's no evidence that students can actually detect the difference between these two types of water. So that's what our experiment yielded in terms of our result. Hope this has been helpful. Again, trying to tie some things together from the beginning of the class with what we're doing now.